All right, guys, so we've just finished solving radical functions. We should now be ready to start talking about graphing radical functions. So we're going to look at really just two types. We're going to look at square roots and cube roots. We're really not going to look at fourth roots and fifth roots. That's just kind of beyond the scope of our class with Honors Algebra 2. And we are going to treat square roots and cube roots a little bit differently as well. Square roots, you should really be able to do by hand. Cube roots with the graphing calculators help. In fact, I'll show you one cube root function by hand and show you kind of how it's similar to a square root. But then for the most part, cube roots and above, just use a graphing calculator for. Square roots, you should at least know how to do those. Let's start just by looking at domain and range. Now it says use interval notation. We really haven't done a whole lot with interval notation this year. So I'm still going to use inequalities for the notation. But if you wanted to use interval notation, there wouldn't be anything necessarily wrong with that in the notes. And as you're practicing, just know that we're going to be using inequalities both on big ideas and on Canvas. So let's go ahead and look at some graphs of the square root function first. In fact, let's just start with the parent function. So we've got y equals the square root of x, which is the graph that I've got for us right now on Desmos. So notice that it looks kind of like this. It's actually a very simple graph. So when we talk about square root graphs, again, that's kind of why we're going to look at them by hand. Is unlike some of the other functions that we've looked at with polynomials and with rational functions, really there's not a whole lot of excitement when it comes to a graph of a radical function. Notice that it does start at 0, 0, which should make sense that you wouldn't have anything to the left of 0 because remember, while the square root of a negative number is a complex value, you're not going to actually see that on a graph of real numbers. So when we're looking at the graph of a square root function, it'll start at 0, 0 and grow to the right of the y-axis, and this is kind of what that looks like. So when you think about the domain of the parent function, it looks like that both x needs to be greater than or equal to 0 and that y needs to be greater than or equal to 0. So again, for that, let me go ahead and copy that down. Here's our parent function, f of x is equal to, then our domain we just said was that x has to be greater than or equal to 0 and that our range has to be that y is greater than or equal to 0 as well. So let's take a look at number 1. We've got y is equal to the square root of x minus 2 plus 3. Let's first just think about transformations. And so when we're thinking about transformations, think of the square root as being your parentheses. That means that on number 1, your function is being shifted to the right by 2 and that it's being shifted up by 3. And let's see if that's actually the case. So if we graph the square root of x minus 2 and then the plus 3 outside of the parentheses, once again, that point that was at 0, 0 is now at the point 2, 3. So it does look as though our graph was shifted to the right by 2 and up by 3. It looks like then our domain is going to be everything greater than or equal to 2. And our range y is going to be everything greater than or equal to positive 3. So let's go ahead and copy those down. So x was greater than or equal to 2. Y was greater than or equal to 3. Which in comparison to our domain and range for our original function, notice that from 0, we were shifted to the right by 2, and from y is greater than or equal to 0, we were shifted up by 3. So really using the domain and range for your parent function, you can talk about the domain and range for your transformed function as well, without necessarily needing to look at the graph. So let's see if we can do that on number 2. So on number 2, we've got some transformations. We do have a number in front of our parent function, which is greater than 1. So we are going to have a vertical stretch by 4. We also have plus 4 inside the radical, so that'll shift it left by 4. And finally, the minus 5 is going to shift it down by 5. So let's see what that looks like on our graph. So we've got 4 in front of our radical. We've got x plus 4 inside of the radical. And then we've got minus 5 outside the radical. And so here is what that graph looks like. So as we expected, it was shifted to the left by 4, down by 5. It also looks like it was stretched. It is growing quite a bit more quickly as you go to the right of the start of the function. But notice that as far as the domain and range, those really don't change because of a stretch or compression. Now they did change because of it being shifted left by 4 and down by 5, but the 4 that was in front of the square root sign really had no impact. And so when we say that it was shifted left by 4, take your domain and shift it left by 4 as well, means that x is now greater than or equal to -4. And for the range, that was shifted down by 5. So for y, we'll also shift that down by 5 and say that y is greater than or equal to -5. So really you can use the function itself, and if you look at it, you can use the transformations to help you with the domain and range for really any square root function. Now let's look at cube roots next. So for cube roots, let's go ahead and just look at the parent function first. So for our parent function, f of x equals x cubed, we get a similar graph. Notice that it does still have a point at 0, 0, and it does still go up and to the right, but now we have this additional piece which is going down and to the left. And the reason for that is you're also able to take the cube root of negative numbers rather than just positive numbers. So you end up with kind of two pieces to a graph instead of just the one piece where the positive numbers were. And if you look at what's happening, it's going to the left forever and to the right forever. So it looks like our domain is going to be all real numbers. Now, while it's not going up and down as quickly as it is left and right, notice that to the left, you are still going down towards negative infinity, and to the right, you are still going up towards positive infinity. So it turns out that the range is also going to be all real numbers. And so again, let me write this maybe off to the side here. For our parent function, f of x equals x cubed, or not x cubed rather, but the cube root of x. Let me write that correctly for us. Then our domain is going to be where x is all real numbers. So again, if you want to use the abbreviation ARN for all real numbers, that would work. And for the range, it would be the exact same thing. So let's see what happens when we use some transformation. So for our first one, we're going to look at where it looks like we were shifted to the left by 2 and down by 3. So again, the same transformations still apply to cubic functions to cube root functions as would square root functions. So plus 2 inside, minus 3 outside looks something like this. So notice that while that does move some of the points around and does kind of shift it down by 3 and to the left by 2, that the domain and range are really going to be the same. You're still going left and right forever. You're still going up and down forever. So our domain and range for this function is also all real numbers. And if you think about it, no matter what transformations you apply, it's still going to be all real numbers, whether you reflect it, shift it up, down, left, right, which means even on something like number 4, where you've got a lot of different transformations, and we aren't going to go through all of them, but it turns out that the domain is also going to be all real numbers, and the range is still going to be all real numbers as well. And so the nice part about cube root functions is that the domain and range do not change based on transformations. They always stay as all real numbers. Okay, so let's look at how you can graph these, and we're going to start with square root functions, and we'll start by graphing them by hand. Now, since they are such simple functions, we're really going to do something very simple for them. We're just going to use an XYT chart. Now, typically when you create an XYT chart, you can pick any numbers you want for X. Now, for square roots, obviously those need to be positive numbers, so like 0, 1, 2, 3, and so on. Now, for the first couple numbers, that'll work. And if we put 0 in for X, the square root of 0 is 0, minus 3 is going to be -3. If we change that to being a positive 1 inside the square root sign, then you have the square root of 1, which is 1, and 1 minus 3 is -2. The problem is going to be when we get to 2, because when we get to 2, the square root of 2 does not simplify. And if we try to take that number, we'll get a decimal, and that's really not something we want to do if we're going to graph this by hand. So 2 probably isn't going to work, and 3 probably won't work. But 4 will, and the reason is because 4 is a perfect square. So really, rather than using just any numbers that we want, 0, 1, 2, 3, 4, what we should really use are perfect squares, like 0 and 1, 4 and 9 and 16 and so on. That way when we put 4 in for our square root, we can actually take the square root of that number. In fact, the square root of 4 is -3, or is +2, and 2 minus 3 is -1. The same is true when we put in 9 for x. When we take the square root of 9, that's 3, and 3 minus 3 is 0. And at this point, you probably noticed a pattern with the y values. They are, in fact, increasing by 1 each time. If you put in 16 for x, you would, in fact, get +1. And now we should be able to go ahead and graph. Now, obviously, some of those won't fit on our graph, but for as many as do fit, let's go ahead and graph those, starting with 0 and -3. 1 and -2, 4 and -1, 9 and 0. That'll be the last one that fits on our graph, so we'll go ahead and just sketch in our function. Make sure to include the arrow pointing that it does continue to the right forever, and there would be our graph. Okay, so let's take a look at number 6. And on number 6, we at least have a better start to this because we can at least go to using our perfect squares rather than trying to use just any old numbers. So 0, 1, 4, 9, 16, and so on. But notice that this time, even those numbers aren't going to work. Like if I try to put in 0, I get 0 minus 5, which is going to be -5 plus 2. And the square root of -5 is not a real number. So that's not going to work. So in fact, we're going to have to do a little bit more to even have some good values for x. And this is where it's good to keep in mind the transformations for your function. Is that if you look at what's inside the radical, the -5 is shifting to the right by 5. So it would only make sense that we would also need to go in and shift all of our x values to the right by 5. And so when we do that, essentially what we are doing is adding 5 to each of our values. And let's see how that helps us with our finding our y values. So instead of putting in 0, if we put 5 in for x, then 5 minus 5 is 0. The square root of 0 is 0, plus 2 is 2. Next, we can put in +6. When we put in 6 for x, we're going to get +1 inside the radical. The square root of 1 is 1, and 1 plus 2 is 3. So there would be our next y value. Next, let's go ahead and plug in 9 for x. So that would be 9 minus 5, which is the square root of 4 plus 2. The square root of 4 is 2, and 2 plus 2 is 4. And actually, at this point, you can probably already notice that similar pattern for the y values. You are going up by 1 each time. So the next y value should be 5, and the last should be 6. Okay, so at this point, let's go ahead and graph our function, starting at the point 5, 2. Next is 6, 3. And the last one that will fit is 9, 4. And we can go ahead and graph our function going through those points. So obviously we saw where we still start with the same perfect squares, but we have to shift them along with our graph. Now something else that we could also kind of discuss is where we start our function. Notice that the first function started at the point 0, -3. If you think about it, think almost as if this square root function were a quadratic, and think about what the vertex would be. Thinking about vertex form, opposite of what's inside the radical is 0, keep what's outside is -3. Well, what about on our next graph? Well, opposite of what is inside the radical is +5. Keep what's outside is +2. And notice that that is also where our t-chart started. So if we think about what it would be in terms of the transformations, that can also be the starting point for our t-chart and for our graph. And so it looks like we're starting to make some more connections. We at least know what to use for the x values, and we actually know what the starting value is for y. The only thing that we have left to figure out is how to know what the y values changed by. Now for the first two examples, they both went up by 1 each time, but that's not always going to be the case, as we're going to see on number 7. So let's take a look at that now. So on number 7, let's go ahead and use some of the information from our function to fill in our t-chart. Again, we will start with the same values, which are the perfect squares, and then we'll look at our transformations to decide how to change those. The plus 3 inside the radical tells us that we're going to shift everything to the left by 3, so we're going to go in and basically subtract 3 from each of our numbers for x. Next, let's go ahead and get our starting point. Remember, to get the starting point, we're going to take the opposite of what's inside the radical, keep what's outside. So that would mean that our graph is going to start at -3, -4. At this point, we're just going to have to go back to the old-fashioned way of putting in numbers to see what the pattern is for the y values. So if we put -2 in for x, that's going to be negative parentheses, -2 plus 3 minus 4, which then when we simplify that, let's see what that gives us. That gives us negative radical 1 minus 4. The square root of 1 is just 1, but there is a negative sign in front, so that's -1 minus 4, and that's going to be -5. Okay, let's do it at least one more time with our next x value, which is +1, and see where that gets us. So if we put +1 in for x, 1 plus 3 is 4. The square root of 4 is 2, but since again there was a negative in front, we need to make it a -2. And -2 minus 4 is -6. There's our next y value. At which point you can probably spot the pattern. Rather than going up by 1, we are going instead down by 1 each time, and here would be our t-chart. So let's go ahead and graph our function starting at -3, -4. The next point would be at -2, -5, then at 1, -6, 6, -7, and finally at 13, -8, we are off of our graph. So we just need to connect our points, and we're done. So what made number 7 different? What was different from it compared to numbers 5 and number 6? And you might be able to spot it more quickly if you look at them all side by side. In fact, the only difference was this negative sign in front of the radical. Well, let's think about what number would be in front of the radical. On number 5, it would have been a +1. And notice that we were going up by 1 for each time we looked at our y values. On number 6, it was the same. We had a +1 in front of our radical, which told us that our y values went up by 1 each time. So then on number 7, where it became a -1, it only makes sense that our y values went down by 1 each time. So let's put it all together. Let's take a look at number 8, and let's see how we can use the different parts of our equation to be able to help us to not only fill in our t-chart, but also to create our graph. Once again, we still start the exact same way as we normally would if we were going to do this by hand. We start with those perfect squares for our x values. Next, we'll look at our transformation inside the radical. It looks as though we're shifting all of those to the right by 4. So that means we're going to go in and essentially add 4 to all of our x values, then shift them all to the right by 4. Next, we'll use the starting point of our function by looking at it in terms of the opposite of what's inside the square root and keeping what's outside. So it looks as though the starting point of our function is going to be 4, 1. And now the final piece, the missing piece that we didn't have before, the number in front of the radical tells us what our y values increase by each time. So it looks as though we're going to add 1/2 to them. I'll do that as a decimal plus 0.5. So that would be 1.5 for the next y value. Another 1/2 would go up to 2, and then 2.5, and then finally to 3. So we've really come a long way. We went from just putting in random numbers for x to knowing which x values to use to still using the function to evaluate. And now we're to a point where without putting a single number into our function, we're ready to go ahead and create our graph. So starting at 4 comma 1, 5 comma 1/2, 8 comma 2, and in fact that's the last one that will fit. Here is our function. Kind of cool to see all those connections just in the course of 4 example problems. Okay, so that's it for square root functions. That should give you kind of everything you would need to be able to graph any square root function that you were given. Let's now talk about cube roots. And this first cube root we'll do by hand. Notice that for the rest, it's just expected that you would use a graphing calculator to find the x-intercepts, the y-intercept, and then to graph the function. So if we were going to do something similar, let's think about what we did for square root functions. And if we were to create an xy t-chart, rather than using perfect squares like 0, 1, 4, 9, and so on, it would actually make more sense to use perfect cubes like 0, 1, 8, and so on. You could use 27, but obviously 27 isn't going to fit. Now notice that I put the 0 in the middle of the t-chart rather than at the beginning. And the reason for that is, remember that cube roots also work for negative numbers. So you could also use -1 and -8 as well. So now let's just go ahead and kind of plug our numbers in. In fact, we can actually use a lot of the same information we used for square roots to also graph a cube root. Meaning that the starting point where we would, or let's start with the shift. We didn't have anything inside the radical, so nothing that we would need to shift by. As far as the starting point, keep what's inside the same, or change what's inside, rather, which there wasn't anything inside, so that's 0. Keep what's outside is 3, so there is our starting point for our cubic table. And then remember, the number in front tells you what you are going up or down by. So starting at 0, you're going up by 1, so that would be 3 plus 1 is 4. 8 plus 1, we're going up by 1 is 5. And then for the other values, instead of going up by 1, to go the opposite direction, you'd have to go down by 1. So that would be 2 and 1. So if we were to graph this function starting at -8, we would be at -1. Then at -1, we would be at +2. At 0, we're at 3. At 1, we're at 4. And at 8, we're at 5. So then here would be our function going through each of those points. And I think I missed that last one. I put it down too low. 8 comma 5 should have been right here. Now we're ready for our function, which will look something kind of like this. Again, make sure to include the arrows showing it going in both directions. And we can actually go ahead and find one of these values. We know the y-intercept is at 0 comma 3. The one thing we don't know is the x-intercept, so let's just go ahead and use Desmos to help us find that. If we're graphing the cube root of x plus 3, here is that function graphed using Desmos, and that'll also give us a chance to check some of our values. So here that is. Again, it does look like we're at 0, 3, at -1 comma 2, and then also at -8 comma -8 +1. So it does look like we went ahead and graphed it correctly. In fact, to find our y-intercept, we're going to have to our x-intercept, we're going to have to go out quite a bit further. And so let's go ahead and do that now. To go all the way out, it looks like our x-intercept is all the way at -27 comma 0. So x-intercept again, -27 comma 0. I also do need to fix my graph. I think I said -8, +1, and graph -8, -1. Man, let's get on top of things. Here we go. Now it should look a little bit more closely to what we used and found on Desmos. Probably would have been best to just have used that in the first place, I guess, at this point. Okay, let's do some more practice problems. Again, just kind of finding x and y intercepts and graphing our function. So on number 10, if we wanted to go ahead and graph at least one point by hand, one point that would be pretty easy to do that with would be to change what's inside, keep what's outside. That becomes kind of the center of our graph. So that's going to be the point 1 comma -2. The rest of the points we can get from our graph on Desmos. Let's go ahead and graph that now. The cube root of x -1, and then a -2 outside. So again, let me zoom out so we can see it. It does look like that center point where we make the change in kind of the shape of the graph is in fact at +1, -2 as we expected. Now we just need to find x and y intercepts. It looks like for the y-intercept, that's at 0, -3. And for the x-intercept, that's at 9, 0. So let's go ahead and graph those points as well. And that should be enough for us to be able to graph our function. So again, x-intercept at 0, -3. Y-intercept, I believe, was at, 9, 0. So let's go ahead and graph those now. So 9, 0 for our x-intercept, 0, -3 for our y-intercept. And again, just draw a sketch of the function then through those points to look something like this. And we're done. So again, if you wanted to graph cubics by hand, you can, but you can see with the graphing calculator and even just some basic information, you can get a pretty decent looking graph just from that. Let's take a look at two last examples of cube root functions, and then that'll be it for graphing. Let's go ahead and once again find kind of our center point where we switch directions. That's going to be at the point -5, -3. So again, change what's inside the radical sign, keep what's outside. So -5 and -3 would be this point right here. And then we'll go ahead and use Desmos to find our x and y intercepts. So let's just change what we had in here to being a -3 outside, a +5 inside. And then it looks like we did have a negative in front. Okay. So, excuse me. Here's what that graph looks like. It looks like we've got some decimals this time, which is okay. We do have a whole number for our x-intercept at -32, 0, and then our y-intercept at 0, -4.71. So again, that's -32, 0. Probably won't be able to graph our x-intercept, but for our y-intercept at -4.71, we should be able to go ahead and graph that at least somewhat close to where it would have been. So right here, and then we'll go ahead and graph our function through those points to look something kind of like this, and we're done. All right, let's take a look at one last example for cube root functions, and that'll be it for today. So we've got 1/2 the cube root of x minus 4 plus 1. Let's again start by just identifying the point where the function switches in its general shape, which again, keep what's outside the radical and change what's inside. That's going to be at the point 4, 1. And then we'll go ahead and use Desmos to find our x and y intercepts. So let's go ahead and change our function to look the way we want it to. So that's 1/2 in front of our cube root, a -4 inside, and then a +1 outside. And here's what that looks like. We can go ahead and zoom in just a little bit. So you can see where our function changes, and that is at the point 4, 1, kind of as we expected based on the equation. And then we can go ahead and find our y-intercept and x-intercept. So x-intercept is at -4, 0. Go ahead and copy that down first. And then y-intercept is at 0, and I believe -2.20 or +0.206 rather. So 0.206. We'll go ahead and graph both of those points. So the y-intercept is just slightly above the x-axis, and the x-intercept is on the x-axis right here. We can go ahead and graph then our function through those as best we can. Very narrow graph, very much a compressed graph, and if you think about it, that 1/2 in front would have been a vertical shrink, so that should kind of make sense. All right, guys, that is it for graphs of radical functions. In fact, that kind of wraps up our part of our unit on radical functions. And the next part, we're going to look at inverse functions, and in particular, how we can compare square root functions to their inverse, which are x squared or quadratic functions, as well as some other inverses as well. Until then, have a good rest of your day.